The last real circuit example representing feedback that we're going to take a look at is this discrete circuit for a current amplifier. So you might recognize this as a common base configuration from ENG 363. And just looking at this initial circuit, it's a little difficult to see how we can relate our feedback equations to this circuit. It's honestly a little difficult for me to see as well. So what we can do to help that a little bit is to redraw our circuit to look like this. So now we can more clearly see up here at this node our KCL relationship between our input, our error signal, and our feedback signal. Another thing that we can see is looking at our collector, we have our output defined coming out of our collector, and we note that our output current is equal to our feedback current. And so just like with our voltage amplifier discrete circuit that we considered, in this case we're going to have a feedback transfer function that's equal to 1. So generally for our ideal feedback, we're taking a scaled version of our output and subtracting that from our input. In this case, we see it's just our output is scaled by 1 as it's sent back to the input. Okay, so our output then, again, we mentioned is our collector current. So for a BJT, so you might have noticed this is a PNP BJT. So typically we'll deal with NPNs, or typically in the past we've dealt with NPNs. But the same operations, the same basic equations hold for PNP as they do for NPN. And so one of those is that our collector current is HFE times our base current. So I naught being our collector current is then equal to HFE times our base current, which is our error current I sub epsilon. Well, from KCL at that highlighted node, we can rewrite our error current, which is our base current, as our input current, I sub I, minus our feedback current. Well, we also just said above that our feedback current is equal to our output current, so we have I in minus I naught, and what we can do is then get our I naughts on the same side, so we have I naught times 1 plus HFE is equal to HFE times our input current. And if we want to solve for our transfer function, we can say our closed loop current gain is equal to our output current divided by our input current. Rearranging our equation above, we have that is HFE divided by 1 plus HFE. And so we see that, as with all of our other circuits that we've looked at, this is the same as our ideal form. And in this case, remember we noted that our beta sub I is equal to 1, and that means that our A sub I, or open loop gain, is equal to HFE to match our sort of standard, our ideal form of AI divided by 1 plus beta I times AI. One thing to note is that we've seen in all of these examples of our op-amp circuits and our discrete circuits that everything is matching exactly with our ideal form. Something to keep in mind, though, is in all of these cases, we've made some idealized assumption. So as an example, if you wanted to look closer at this circuit, you could look at page 882 in the Neiman textbook. And what we could see is if we add an emitter resistor, R sub E, that's going to introduce loading effects and cause us to deviate from this ideal model. So again, one reason why we might want to add that RE we looked at in ENG 363, so that can help us bias our transistor in the forward active mode. But again, that causes us to then deviate from this ideal form. So keep in mind that a lot of times what we're doing in this class is we're making assumptions. We get some equation that is a good first approximation. In many cases, that's going to be good for what we're doing, but in some cases, we might want to come back to that with simulation or a more detailed calculation in order to get a more accurate picture of what it is we're trying to calculate.